So let's start with today's lecture. So what we do today is we will again look at the atmospheric neutrinos and its solution, but now we look at it more quantitatively, some details. Then we will look at other experiments which we have done to confirm oscillation, the so-called short baseline experiments, where we actually created neutrinos of a given spectrum. We detected their energy. And then we will go to see if there are any other alternatives apart from neutrino oscillations which can help you in resolve the atmospheric neutrino. Okay? So there will be some candidates and we try to do them. Okay? So that's what we will do. So let's now go back to atmospheric neutrinos and try to see quantitatively what we can see. Okay. So to remind you of what we had, this was the zenith angular dependence, electrons, muons, low energies and high energies. Okay. And we remember what the law is. So we saw that neutrino flavors mix and they have different masses and the oscillations are only between nu, mu and nu tau. We satisfy all the requirements of atmospheric neutrino. And in fact, if we start with simple quantum mechanics and give particles masses, we get this simple formula with the oscillation. So now we have to find out. So we say that oscillation gives better solution. So we have to figure out what is this better solution. In what sense it is better. Okay. Just by eye, okay, no, I may be able to say that I looked at this plot.
One oscillation plot. You are making two neutrinos like that.
Two neutrinos will come later. Right? At this point, you can take it from me that effect of 3 neutrinos is a very small effect. So at the level that we have been doing things at this moment, we don't need to consider 3 neutrinos. We will come to 3 neutrinos after maybe 4 more weeks. That will affect it. It's going to be important.
So these data points, they subtract any kind of backgrounds or
after subtracting background.
Oh, this is after subtracting.
Yeah. And the errors that come from the background are reflected in this error bar. So the error bar actually involves both. It involves statistical error as well as the so-called systematic error. Systematic error means that all these things, no? Error that comes from subtraction of background and so on. I'll also tell you about some more errors.
No, just coming back to this question. See, I'm just thinking, even if some scattering inside the earth or something happens, that will be most likely spherical symmetry.
Possible, but I suspect that actually will not come to play at all. My claim is that the neutrinos that come out from these decays of moons inside the Earth are going to be asymptotic. And so, not asymptotic. The main reason is they have very low energy neutrinos, and you won't see them here at all.
So I'm asking that because for high energy muons, it just enters the arc. As muon going to neutrino cross section is not very small, there will always be some neutrinos which will gain from high energy muons.
Such background will always exist. Okay, and we trust the experiment to take care of this background.
So this data.
So, for example, I know this background is important. This has to be taken care of. The reason you go to 1,000 kilometers inside the Earth is because such background is minimized. So, in fact, in 1,000 kilometers inside the Earth sort of corresponds to reducing the background by some factor of 10 power minus 8 minus. Okay, that's why you're inside the Earth. So, mean free path of muons inside the Earth is of the order of tens of meters or so, like this. And 1,000 kilometers, therefore, many lifetimes. Therefore, you expect that all these muons that actually came decay away before reaching. So this background does form. This does form part of the background. Okay, but then that is decayed. So we are not 1,000 meters. 1,000 meters. Order of magnitude. Don't take it from me. I have to look at the number somewhere and then. I think it has 1,000 meters. 1,000 kilometers is like. I'm sorry. Sorry. No, 1,000 meters. No, 1,000 meters. 1 kilometer. Okay. So next thing you want to do is you want to quantify what you mean by saying oscillation swift. Okay. So till now we looked at things qualitatively. We said okay, fine. No? Some muons are lost. So we want to be slightly more quantitative. So here, for example, we knew that this solution is bad without oscillations because the data is very far away from it. And quantifications of that means that you look at the data, look at the predictions, and then you find how different is the prediction from the data. Okay. There are now sophisticated techniques for doing this, but let me just tell you about a simple, straightforward method with which you can get to first order reasonably good answers. Okay. I suspect many of you have already done some experimental physics to know about chi-square. People know what chi-square is? Okay, good. So then I don't need to tell you what chi-square is, I just need to show you the application. So what do? So what we have done here, so the data is available in bins. Bin means the cosine theta between 1 and 0.9, 0.9 and 0.8 and so on. So in each bin, you have to predict something. So you predict number of neutrinos, which I call it as Ni theoretic. Then you measure something which is Nr experimental. Sigma I is the error. Okay. So error somehow should combine error in experiment and an error in theory. So right now let's do a very assume a very simple thing where you know what the sigma I is for each bin. That is what involves a lot of experimental work, a lot of analysis actually goes in figuring out what is sigma I. That's perhaps the most difficult part of experimental analysis. But let's say that we know what the sigma is and we know what is Ni experimental. Now our job is to figure out what is Ni theory is, what is expected. So normally one would say that you simply start with the flux of it. So what one would say is someone tells me what is the flux of muon neutrinos. Okay. So let me call that as, let's say I want to find out final flux of muon neutrinos. Now this flux can be a function of energy of this neutrino and of the zenith. So I would say, okay, fine. So this flux came to me from two means. Firstly, some muon neutrino flux came in and it survived as muon neutrino. So there was some muon neutrino flux initially, so phi mu 0. This was also a function of E mu and a function of this zenith. Some of them survived. Okay. So the fraction of the neutrino surviving was probability of muon neutrino remaining as muon neutrino. This probability depends on energy, depends on the angle. Okay. So this is in E mu. This zenith angle. Zenith angle determines the length traveled through the earth. So that is your L. Very good. Okay. So therefore, this is the flux of muons that came from initial muon neutrinos. Plus, there was electron neutrino flux. So there was this flux of electron neutrinos. E0 the function of and then there was some probability that these electron neutrinos became muon neutrinos. It's possible. This again will be a function of E mu and
but we haven't considered the electron neutrino converting into muon neutrino.
Yeah. So then, since we now sort of know to our first observation that electron neutrino don't participate in the oscillations, this would mean that this PE mu is 0. So plus in general, there could be a tau neutrino flux, although in general there is no tau neutrino. So again you have a tau neutrino flux. So maybe I shall write for completeness. Oh, this is E, sorry. E, E, and then this will be E tau, tau, E tau mu, E tau. In atmosphere there is not much tau flux, so this won't matter.
Yeah. In the experimental plots, the theta beams are same for low energy and high energy.
Yes. Ask me the same question after 10 minutes, because that's what I will do.
Because for low energy neutrinos, measuring theta is difficult.
Yes. Okay. So in general, okay, to be able to for finding the flux of neutrinos, this is what you would want to do. Okay. So atmosphere big neutrinos, we know that it's mainly the first line that will come. The rest we don't. But when you are, for example, making a beam of neutrinos, you might make a beam of electron neutrinos. You may make a beam of tau neutrinos. I don't know if you want to make this. Okay. However, this is the flux that will come to the digit. Okay, so flux will mainly involve the initial flux of muons at time this E mu. So let me write it here. As I am writing it, it's phi mu 0 function of E mu theta mu times E mu mu. This is the flux that is detected. Now what happens? We can't measure this flux because you can't see neutrinos. You look at neutrinos through the production of leptons, charged leptons. This produces muons. So in the detector, the neutrinos will come, produce some muon. Okay. Neutrino is going to come at an angle of theta, but the muon will go off at some other angle. Okay. So actually let me be slightly more specific. Let me call this as E of mu. So if you forget this, go to be more exact. Let me call this flux mu 0 of E mu theta mu. Then there is P mu depends on E mu. So at this point, therefore, what we have is a flux of muons with this energy and this. Now these muons will convert to muons with some cross section. If the cross section is more, you absorb more muons. If it is less, you absorb less. Also, when the electron is produced, the muon is produced, it will change the energy. It will also change the angle. It will change both. Okay. So what we need therefore is a distribution. So now what's going to happen is, if we write it down and tell you where this term comes. So this is E2 sigma by DE mu E cos. Okay. Now this E mu is the energy of the muon coming out. Okay. And this E cos theta mu is the angle of the muon coming out. In general may be different. So what is this? This reaction is mu plus some nucleon going to some muon, so mu plus mu minus, and some other nucleon. Okay, it would have converted to be proton by became this mu is energy of mu and theta of mu. This has energy of muon and theta. So the detector, what happens in the first stage is nu is converted to muon. So at this stage, therefore, what you have are muons, okay, and these muons are characterized by E mu and theta mu. Okay. E mu can be different from E mu and theta mu. All this information is going to be contained in this differential cross section. So this is a very important point. Differential cross section. It depends on all these factors. A lot of effort goes in calculating this cross section. Okay. Also experimentally, there are experiments which only talk about measuring this cross section. We'll come to that at some point. So now we have come to a state where we produced muon. However, so now you want to measure what is the energy of muon and what is the angle that this muon is. However, experiments are never accurate. There is always some error involved in measuring energy of muon. Okay, energy of muon is 1 GeV and its error is 10%. It can be anywhere between 900 to, you can measure anywhere between 900 MeV to 1.1 GeV. So this error has to be incorporated in our calculations. So therefore, we have what's called as a resolution function. This depends on theta mu, which is the actual theta of the muon, and theta mu I, which is, let me call it m. M is for instance tilde. Theta mu tilde is the measured angle of the muon. Okay, it may be different from actual theta. So what does this mean? For example, let's say there is a Gaussian distribution. So let me give one example. So this R of theta mu tilde may be e to the power minus of theta mu minus theta mu tilde square by some, for example. This is the Gaussian error. So this means that if the error is, this will look like Gaussian. This is the Gaussian. So this is theta mu. This value is theta mu tilde. So although actually value is theta mu, you need not measure that value. You can measure a value which is slightly greater or slightly smaller. So another thing that an experiment is going to do is to figure out what is this function for the R theta mu theta mu. Similarly, there is another function for E. Here, you go in 3 steps. Go from E and theta for neutrino to a E and theta for the muon to the E and theta, which are the actual measured quantities, which are these detailed at the right. So what this will give you, now I'll come to the left hand side, is the number of neutrinos. Number of neutrinos as a function of mu tilde and in an experiment, what we measure is this one. So finally you will measure what data is going to be the measured energy of muon, the measured angle of muon. That's it. Therefore you need to compute the expected measured value of muon and expected measured value of xi. So you will measure actually E mu tilde and theta mu. So what you see there in the plot, okay, actually is not the zenith angle. this theta actually is theta neutrino. The measure, of course, you can only measure angle. You can say nothing about actual. Energy, again, there is some resolution, but here, since you separate things into low energy and high energy, there is some problem on the borderline to figure out which events go in the multi-GV, which go in sub-GV. Okay, but as long as away from the borderline, you are perfect. Okay. However, this is just to emphasize that what we actually measure in this theoretical number is this whole quantity. Out of this quantity, this flux is something that is given to you by people who are experts in calculating flux atmospheric. This is information about cosmic rays, about atmospheric cross sections, and so on. So this is that what atmospheric flux people will do. This is what we calculate. So this course will teach you about this E mu. This part is what nuclear physics people give. You can done that calculation of nuclear physics people plus some experiments which can take you normalize this. These resolution functions are a function of the experiment. So the actual individual experiment will tell you what its resolution function is. So here comes the equivalence point comes into play. If the angle is, if the energy is very large, it's more easy to construct the incoming energy of neutrino. So for example, it's like this. Let's say if your neutrino has energy of, let's say, 100 GeV, very high energy. This hits a proton. Very likely, the muon that goes out will go in almost the same direction as the incoming neutrino. Okay. So if you are at very high energies, you reconstruct the energy of neutrino very accurately. So you are very safe. On the other hand, let's say you have a 10 eV neutrino. So it's not here, but it's say 10 eV neutrino, like the solar neutrino. Now 10 eV neutrino, let's say it hits a proton. It's 1 GeV. So proton is much heavier than the neutrino. So you can imagine what happens when a small ball hits a big ball, right? It just bounces off. And this guy moves very little. So in the direction of this bouncing ball tells you almost nothing about the direction in which the earlier ball came. So when you have low energy neutrinos, the information about incoming direction of neutrino is much less. When you have high energy neutrino, the information about incoming neutrino direction is much more. It's again a rule of thumb. So finally you will be computing this. So out of all these different factors that influence the final prediction, this course will talk only about this. For the rest, you have to take some other courses. So I will not teach you those things. But this is important. So we'll assume that everything else is somehow monotonous. So you should keep that in mind when you go to real world. So now what we will do is we will try to find the value of chi-square. Okay. So people know about chi-square per degree of freedom. Okay, so let me just say it. So this is the way we calculate chi-square. Now, if things were perfectly fine, all the letters were together and so on, we expect that number of chi-square is this number chi-square is nearly equal to number of points you have. Not strictly true. Strict statement is chi-square is nearly equal to number of degrees of freedom you have. Degrees of freedom is equal to number of points minus number of free parameters. So let me.
Yes, variance we are taking into account your resolution function.
Yes. So number of degrees of freedom is equal to number of data points. Just minus number of parameters. Okay. That's because if you try to use more parameters for your fitting, you can decrease your chi-square. You can of course create a curve which goes exactly to these points by some complicated theory, and you say my chi-square is 0. This has no meaning. Right? So somewhere you have to pay this payment. So there is a rigorous statistical way of showing why this actually works. Rule of thumb is the following. The rule of thumb is that the chi-square that you get divided by degrees of freedom, so we should be called as QF, should be of the order of. This is a reasonably good statement if all your errors are statistical only. Usually there are also systematic errors. Okay, but let's try to understand things in this way. Yeah, you have the question.
Yes, so the theta which the experimental plot, so it's the theta of the Muon.
Major theta of Muon. It's theta mu tilde in our report.
So for high energies, you can just take it as the theta of the neutrino coming in.
But you don't take it to be like this. What you do exactly is this. You follow this procedure and you see what you get. And that's what you should. This is the state class.
Okay.
So our arguments about high energy being better resolved is all incorporated into this. This and R. So R will give you this function.
Yeah, so there is some function which converts theta mu to theta nu.
Theta mu tilde. This one. Major energy. Yeah, I want everything to be very clear about this. There are three energies here and three angles. Energy of mu, energy of muon, measured energy of muon. You have angle of mu, angle of muon, measured angle of muon. These three are different quantities. Right? So this is what you expect. And you can even say that if you find what is chi-square per degree of freedom is, that sort of gives you the sort of so-called number of sigmas by which your measurement is away from the expected. Okay. So 1 sigma is fine, 2 sigma is okay, 3 sigma equals bad, if it's 5 sigma, your fit is not good at all. This is a basic rule of thumb. Okay. And then you can go to details. Anyway, when the INO guys actually do the fits, they will involve even more involved algorithm. But at least for this moment, this is a good rule of thumb. So with this rule of thumb, I'll actually show you the first slide that was shown in the conference, which declared that Neutrino was. It's a good transparency to have. So the first one was shown in 1998 by Tata. Okay. So this is in some sense the most famous slide. So let me show you what this slide shows. Okay, let's go over this. So these are both fully contained events. The electron-like events. These are muon-like events. Okay. Right now they have not been separated into low energy and high energy. They have been combined. Okay, because this was just preliminary. So again you will see that this emsing is Monte Carlo, which is predictions. Okay, so after doing all these things that I said in the last 10 minutes, you found out this n of E mu tilde theta nu tilde. That gives you these expected predictions, these values. The crosses are data points. So now what you do is you try to find out the value of chi-square. Okay. So if you look at the value of chi-square here, okay, it turns out that the value actually happened to be of the order of 2.2. There's some slight maybe later you can say. So the chi-square here is not simply equal to this base, the experimental minus theoretical. There is some normalization involved, okay, which means that I have this theoretical band of this Monte Carlo, but all these points can go up or down by the same amount. Okay, that's because I don't know my cross section field, or I don't know initial flux field. So this is a free parameter. Okay. So you will notice that although number of points here is 5, number of degrees of freedom is taken to be 4. The reason being that you can actually shift things up or down. So if you look at this electron data, you will find that the data is actually slightly higher than this predicted. However, the prediction is subject to normalization, So all the data points, the prediction points, actually will be shifted slightly up back to the data. So therefore, what is called here is chi-square into bracket shape. Okay. So this tells you how good the shape is, and not how good normalization. You can do this thing. If you are confident about normalization, you can able to normalization. Okay. However, the flux at that point of time was known only to about 30%. Okay. So if you introduce 30%, then of course these errors will become rather large and you will be able to say nothing. However, the shape was known well, because remember the shape is mainly dependent on our arguments like gamma factor, the length of atmosphere and so on. Okay. So therefore, shape is known well. So error in the shape is therefore small. Okay. So if you allow yourself to change the normalization, you can try to match this data almost exactly. When this was done, it was found that the value of chi-square was 2.2 for the electron. Okay. And 2.8 by 4 is 0.7. It's a small enough number of the order of 1. This shows you that the data and the expected values match reasonably well. Okay. Which means that electrons don't give you any problems. Okay. New data is reasonably okay with it. So this is quantitatively how you say that this data is flexible. Now let's go to muon events. In muons, you will see that the shape of the predicted number of events is in fact very different from the shape of what you expect. What is observed. So what is observed is actually very asymmetric. What is expected is symmetric. So even when you computed only chi-square in shape, the number turns out to be 30. Okay. So 30 by 4 degrees of freedom is of the order of 7.5. Okay. So it's like in vague terms. You can say it's 7.5 sigma. Chi-square is 7.5, large number. Normally, if your chi-square is more than 2, you should doubt your fields. Okay. 7.5 is the large number. So this large chi-square tells us that there is something really bad with this data. What they also computed is over up-down asymmetries. It is one way of finding out what a shape is. So therefore, for up-down asymmetry means that you look at events in these two bins, sum them up. You call them down events. They are coming from. You forget about the central bin. Because central bin is horizontal events, so you don't want to take them. These two bins are up events, so they are coming up. You measure up-down asymmetry. We expect that this asymmetry should be 0, essentially. If you look at mu events, okay, so the ratio should be equal to 1. Asymmetry is 0. So on mu events, ratio is 0.93 plus minus 0.12. So consistent with 1. Okay, which means up events is equal to down events. Hypothesis is not ruled out. So mu don't give us any problem. Mu is fine. Now if you go to mu, you find that the up and down number of events. So up events is 139, down events is 256. Okay. So that number is of the order of 0.5. Okay, much further away from 1. To claim that it's not consistent with 1, we have to see what the errors on these events are. Okay, so there should be some error associated with this 0.5. These are the details of the errors that were given in the slide. This again comes from the experiment. Okay. Turns out the errors were 0.54, errors were plus minus about 0.05. Now with these errors, it's very clear that the point of 1 is very far away. Okay. So if you take, for example, this 0.06, let's say take 0.05, and you are away by some 0.45, so you are sufficiently far. So again, this tells you that up-down asymmetry tells you that the ratio is not equal to 1, with very good accuracy, and therefore Muon neutrino data at some point. So any time that you will do an experiment, do the analysis, you will come across this chi-square and you end up doing this analysis. Has everyone done chi-square at some point of time in some course? If not, and you are doing experimental physics course, you should ask someone to calculate chi-square. I'll give you a problem to do chi-square. Okay, so now this was chi-square. Okay, by just given input flux to show that the data doesn't conform with what we have. Now we want to check that your hypothesis of neutrino oscillations actually reduces this chi-square to a very small value. This is what you want to do. Okay. So therefore, now you will introduce your probabilities, your P mu mu. So this chi-square was calculated by using P mu mu equal to 1, with just input mu1. Right? When you say no oscillations, it means that this factor is equal to 1. Now you want to put in this factor and see whether this chi-square can be reduced. So you put in this factor. This factor depends on two quantities. It depends on delta m square, depends on the mixing angle theta. Delta mixing. So therefore, your chi-square, so your chi-square is actually going to be a function of delta m square and mixing angle theta. So let me call it theta mixing. So this means that for each value of delta m square and each value of theta, we will find some value of chi-square. Okay, this is clear, right? So these two are your parameters, delta m square and theta. So you go over the whole range of allowed values of theta, whole range of allowed values of delta m square. For each of these values, you find a value of chi-square. Okay. Then you go to that point where chi-square is minimum. That is your base fit point. So normally what you will get, so first thing we do is, let me put this slide and this. So what do you do? You take the whole range of theta. It's a range of sin square to theta, because in oscillation formula we get sin square to theta. You go to a relevant range of delta m square. And then you find out at which point your chi-square is minimum. That we call as base fit point. So this is the base fit point. Now around the base fit point, now you see what happens when the chi-square is slightly more than 2. Statistics will tell you how to figure out the points and relate them to what are called as confidence levels. So people are familiar with confidence levels. So let me tell you the meaning of confidence level. So base fit point is here, but base fit point tells you nothing. Not just a single point. Okay. What is important is to find out the range in the parameter space, okay, which are the so-called confidence levels. Okay, so let me tell you what this means. This innermost curve, this red curve, you can see the color, right? It's called as 68% confidence level. Now what this means is, if I do the same experiment 100 times, 68 times, I expect to find my answer within this. Outer curve is black curve. It means that if I do the experiment 100 times, 90 times I will find my base fit value within this curve. And this dotted curve is 99%, which means that 99 times I will find my value. So first you decide what you want to say. Let's say I want to tell you with 99% confidence as to what the value of delta m square and theta is. Okay. So then I give you this 99% curve. And I tell you that you do the experiment again at some other place. You do hundreds of experiments, and 100 of you do 100 experiments. 99 of you will find the values of delta m square and theta within this contour range, so within this range. So what number to give depends on your taste. If you give 99% number, people will believe you more, because you are giving a large confidence. If you tell 68% level, people say okay, but they will believe you less. 68% is often also called as 1 sigma. Okay. The reason is that if you draw a Gaussian, and if you go away by 1 sigma, then the area between these two regions is nearly 68%. You have a more accurate number? Whatever. That's why people often use 68%. Okay? 90%, if you want the area to be 90%, this usually corresponds to 1.6. Good numbers to know. If you have 95%, that's nearly 2 sigma. And 3 sigma is 99 point something percent. I forget what it is. That's more than 99%. So people usually talk in these two terms. Talk about either confidence level, 68%, 90%, or in terms of sigma. So actually, what was shown is this transparency. So this 6.2 sigma, it could actually correspond to some confidence level, okay, which would be much larger than 99%. Right? So when these fits were done, and doing the fitting was much more than what I showed you now. With what I showed you now, and with the data that I showed you, you can get reasonable fits. It's not that big a deal. Okay? Just that to get the fits more accurately, you need to know a lot more than what I already showed. Okay, so you can do 12 fits with whatever I showed you, and you will get answers consistent with this. However, you are not going to get such small ranges for your allowed. You will get much larger ranges. Errors will be large. So when this analysis was done, it was found that if you look at this 99% confidence level, the value of delta M square, it's called delta M square atmospheric, is between 1.3 to 3.4 times 10 power minus 3 electron volts. So this range. Okay, unfortunately I can't draw on this. So, and these numbers are something that should be reasonably ingrained in mind. So at least one should know that for atmospheric neutrinos, delta M square is of the order of some 2.5 times 10 power minus 3 electron volts. Okay, because you will come across this 167. If you look at mixing angle, you see that the best fit mixing angle is at sin square 2 theta of 1, which is 45 degrees. Okay. However, as I mentioned before, best fit has no meaning, just some number. What's important is to 99% confidence level, how confidently can you want to be 99% confidence, right? What can be the range of theta that you can make? So that range corresponds to this. Sin square 2 theta should be more than 85.85. Okay. And for this thing, you will find that the mixing angle range comes to be between 36 degrees and 54. It's symmetric. Okay, so it's 9 degrees this way. Okay. So therefore, although here I will mention many times in this course, say that atmospheric mixing angle is maximum, is 45 degrees. That's not entirely true. It's anywhere between 36 degrees and 54. Okay. So this is the accuracy to which we know the answer at this point. This is the quantitative way of actually saying something about it. So we will, therefore, try to measure parameters allowed in this parameter space by many experiments, and we expect that almost always we will.
When they quoted a 6.2 sigma, what would that correspond to?
So 6.2 perhaps would correspond to some 99.999, so whatever. Okay. So 3 sigma is 99.87. 6 sigma perhaps correspond to something like 1 minus 10 to the power minus 6 or something like that. But it's, see, if you go beyond 4, or 5 is already here. It just e to the power minus 6 sigma is 36. E power minus 36, whatever that means. So I have some references here. So you can go and try to look at this. This was the first paper that came out in 98. It declared that neutrino oscillate, therefore they have a mass. These are two of the most recent publications of superconductor. This one in particular will give you a lot of information about these resolution functions and all such things are involved in experiment about which only superconductor people will know. These are some of the latest results. This is the paper that does an analysis of atmospheric neutrino with 3 flavors. So at this point, perhaps you don't need to read this paper, but I have it here for completeness. So at some point, we have to come back and we have a look at this paper. Because that is again very important here. So this was the quantitative treatment of atmospheric neutrino. So let me give you maybe 30 seconds of demonstration. So things are simple, but it's important to be clear because you usually don't find a textbook which will give you all this in the written form. So mainly things that you get by perhaps listening to people in class. Okay, so let's go to the next step. So of course we looked at atmospheric neutrinos. We saw there was a puzzle. We showed that if we fit that with our hypothesis of oscillations, chi-square gets reduced and you get some good solution in some values of delta square and theta. Still, you are a bit edgy because you don't know the source that well. Okay? Because for this analysis, I needed to know the flux of neutrinos. Okay? Someone else did the calculations and they gave flux of neutrinos. Okay? This was dependent on many things. It depended on something that the cosmically people tell me. It depends on the structure of stratosphere, ionosphere, I don't know what, elemental composition there, which I am not sure about. However, I trust what they tell me, therefore I get this. Okay, so I am still slightly shaky. To confirm this, what I need to do is, I should have a source which I know well. I should know that this source will give me this spectrum of neutrinos. Okay. Then I have this source, I let my neutrinos travel a certain distance, I detect the number of neutrinos, then I see what happens, then I go through my chi-square thing again, and then if that gives me the same answer as what I had earlier, then my analysis is confirmed. Okay, till that point I still depend on absolute people. Okay, and particle physics absolute people always have this facility with them. None of them believes others. So therefore, it was important that to design an experiment, we should be able to confirm these values. So how do you design an experiment? Okay. First thing to do is to come to the ground level. The first thing to do by coming to ground level is come from the natural units to units like kilometers and meters and degrees. So this formula, for example, is in natural units, which means h cross is equal to 1, c is equal to 1, okay, and so on. Okay. It's good to come to natural units. No substitute for h cross in whatever electron volts per number. So you do this. Once you do that, you will get to this level. Okay, so I'll give you something ready-made, but you can already test this. So what does this mean? This probability is given by this formula, the factor of 1.27, that comes from unique convergence factors. So now all you have to do is, you write delta N square in electron volt square, always. Okay? So if it's atmospheric, you just write 2.5 times 10 to the minus 3. Okay? The length, you write in kilometers. And energy, you write in G. Once you do this, you just have to multiply this with that factor 1.20. Okay? So this is the form that people use practically. Okay, when we actually are doing simulation. So now you have this formula. Now you want to design an experiment to be able to do this. So how will you do this? See, sin square 2 theta is not in your hands. Okay, it's just something that is there. This term is oscillating term. It's a delta m square L and E. But delta m square is not in your hands. But you know its value approximately. A is in your hands, E is in your hands. So we can adjust L and E very easily. What is a good experiment? A good experiment will make sure that oscillations are very large. Okay? So you should make sure that this quantity, the second term, should be large. So as close to 1 as possible. Okay? So you want this inside part to be close to 1. Okay? So which means that what I want is 1.27 delta x square, electron volt square, L by E. Okay. Should be of the order of pi by 2. Pi by 2. Okay. Now we are going to test atmospheric neutrinos. So I know what delta x square is approximately, some range. It's 2.5 times 10 to the minus 3. Okay. So this is 1.27 times 2.5 times 10 to the minus 3 times L by E should be close to, so what is pi by 2? 2.5. 1.5. Okay. So now you can tell me what L by E is. Okay. So this A is kilometers. Okay. So let's see. Can someone do the calculation? Just do something. I will do what I often end up doing. So it is 1.5 times 1.3, 1.27 times 2.5. So what it is? I cancel this, and this gives me 400. 400.
Have you taken the 4 E thing?
Yeah. So this 4 is taken up. So
In 1.27?
yeah. Okay. So 1.27 includes 4. 470. So 400. So let's check 500. 500 is. What this means is that if I have a 1 GVT, okay. So I have freedom in choosing L over E. Okay. But experimentally I have limitations. I cannot produce a beam of some PeV neutrino. It's very hard. GeV is simple. Okay. Secondly, also distance L. Okay. It's easy to make an experiment, with of course with 1 meter. Yes, it's very easy. But with 1 meter, you will find that if it's 1 meter, if this is 500, you need like what is the energy that you need?
500.
If I have a 1 meter experiment, age is 1 meter.
1000 times 500.
So 1 meter by 1 by 400 GeV. Or what NeV. Okay, so I need much smaller than NeV neutrino. Okay, not good. Okay, NeV neutrinos are not very good to handle. Neutrinos are good to handle at 1 GeV neutrino. Okay, and if I have 1 GeV neutrino, my length should be of the order of 500 kilometers. So this is the approximate range. Okay, of course my beam is not going to have exact fixed energy. It will vary a factor of 2. So then now depending on which mountain you get to have an detector under and which source you get to have an accelerator from muons, you choose a compromise situation. Okay. So the first compromise situation for the chooser was the experiment called K2K. So KEK is an accelerator in Japan, the same one which had B factories and which had been given Nobel Prize last year. So this would make neutrino. Okay. Kamiokande was the detector, which is already present. Therefore, it was easy to just make a beam at KEK sent to Kamiokande. The distance was fixed, 25 kilometers. You could do nothing to it because that is the distance. Energy of beam, it's reasonably good to make beams of the order of 1 GeV, as I mentioned. Okay, this comes from experimental considerations, okay, not from any theory. So you can see these numbers, right? 0 GeV, 1 GeV, 2 GeV, and so on. So this was the beam that they had. So that beam, that curve gives you the flux of neutrinos. No, calculated. That gives calculated. The experimental data is those bars that you see. If you had calculated chi-square with no oscillations, you would have got very large chi-squares. I don't know the numbers, I won't give you. However, if you try to introduce this oscillation hypothesis to some data and square and theta, the minimum value of chi-square is obtained for some parameters, and those parameters give you the rate curve. Okay. So this says the best fit spectrum with neutrino oscillations. Best curve is this, and the chi-square is this level. So now, with this K2K experiment, you have found out what is the range of delta m square and theta. Next step you want to do is you want to check if your range is consistent with what you find from atmospheric neutrinos. Then only you are confident. So look at this range. This green part is the 90% range of K2K. The black part, that curve, is 90% range of atmospheric neutrinos. And they overlap. Yes, it was very essential that they actually overlap. Okay. So now we know that these two experiments are consistent. Therefore, perhaps at what the astrophysicists were telling me was correct. Astrophysicists and atmospheric people. Atmospheric sciences.
How are neutrinos produced?
The main way to produce pions. How to produce pions? Take protons, accelerate them, hit on target. This is the simplest way to produce anything. Take protons, accelerate protons, hit on the target. Then produce pions. Okay. So take pions out. Pions will decay to muons. Muons will decay to nu. Okay. So you will do something to separate out only pions and throw away kaons and so on. Those things are details. This is the process. That's why making a muon beam is very, very easy. To some extent. So K2K was the one which confirmed this for the first time. Another important experiment which is going on till now is called MINOS. This starts from Fermi Lab and it goes to Sudan mine in Minnesota. This distance is about 700 kilometers. Okay, so now you can see our estimates were 1 GeV is 500 kilometers. So 750 kilometers is 1.5 GeV. These back of the envelope rules of thumb should be sort of in your mind, because then it will help you get an idea of them. Therefore, we expect that you will get the maximum signal at 1.5 GeV. Of course, no, in making a beam, you have other considerations. So you can't always make a beam which peaks at 1.5 GeV. But they had a beam which peaked at about maybe 3 to 4 GeV. So this dotted things that you see was the actual beam. No oscillation. These are data points, and if you see near 1 or 2 GeV, you see that data points are really, really low. Okay, almost a matter of 2 atoms.
So if we see the up beam, up muon neutrinos and down muon neutrinos, and we vary the Janite higher, then the ratio should also be the up flux and the down flux should also be oscillatory in nature if neutrino oscillates. Because the length we are varying.
Yes. And the reason it doesn't happen is because of energy resolution. So we will come to that.
Okay.
So I actually ask you to plot what up-down ratio looks like. But this question was for atmospheric neutrinos, right? Not for this.
No, not for this.
Not for this. Here, of course, you know where the beam is coming.
Yeah.
Atmospheric, yes. You are correct. In principle, it will be oscillatory in nature. Okay, but as you will see, because of energy resolution, things get averaged out. Therefore, what we see superconductor is not oscillating. Okay, but in principle, yes, in design experiments, where you can see some oscillatory. Okay, we'll come to that. In fact, I know at some point of time does want to see these oscillations. Okay. So coming back to this is the luminous detector, and you will see that indeed around 2 GeV or so, data point is here, and expected value is somewhere here. So it's almost a factor of 2 or 3. So again, you do independently a Caspian analysis for this particular neutrino beam, and you get your own confidence points. These are the Minos confidence points. So let me see. This dark blue line, dark black line, this edge of this colored area is Minos 90% confidence. Okay. Now you see that this faint blue line is the K2K 90%. Then this blue line here is super commutator 90%. So they overlap. This red line is another analysis of super commutator, which is more analysis called L by D. I will mention that. Okay. So all the analysis now converge on exactly this kind of parameter space. Therefore, we are confident that this is the parameter space which actually is there. So let me again wait for some So in the atmosphere, we saw how they fit. We saw the spatial analysis works, and then we went and did 2 experiments in which we actually managed to the initial neutrino spectra, final neutrino spectra, and saw that oscillation analysis actually works. So maybe I will stop here, because I think it's too late in the day. Must have attended some higher lectures today. So alternative solutions I will talk about in the next class. Next week we will have no classes, and in fact Monday after that, which is March 1st, is also a holiday. So next class is going to be on March 2nd. Okay. However, within the next 2 days, in fact perhaps just tomorrow, I will send you your first assignment. Then you have a long time. So right from this time.